Hello and welcome back. Okay, so I've done a little bit of work on here, cleaning up some of the dodgy joints, and I've got things absolutely stable again. I've even managed to get rid of the last glitches over here. So let's run what I've currently got. So this is the Fibonacci sequence in 16 bits that I've demonstrated before. Now this is outputting in hexadecimal at the moment, which is great from a programming perspective, but it's not very satisfying to look at. So one of the things I've said I want to do is write the code for a binary to decimal conversion routine, and to do that I need a divide, and that's mostly what this video is going to be about. Now I do appreciate that not everyone wants to watch big long programming videos, so I'll put the time index down here for the final demonstration and you can jump to it and have a look at that. And I think I probably need to start off with a description of how we're going to go about a general purpose divide operation, because I've seen a couple of people working on homemade 8-bit CPUs who've done it a little bit inefficiently. Now I'm sure everyone watching this has done long division before, but I'd like to explain it in a specific way that will make things easier as we move towards coding it up in assembly language. So this number here is the numerator. Sometimes you'll see this called the dividend. This number over here is the denominator. You'll also see it called the divisor. But basically, this is just the long division notation for saying we're dividing 273 by 12. Now the first thing we want to do is look at the first digit. We're going to bring it down here, and we're going to call this section down here the remainder. This might not be how you've seen it done before, but bear with me, it will make sense by the time we get to the end. If 12 were to go into 2, we'd be putting that up here. But as it is, it doesn't go in, so we're going to put a 0 up the top. Then we move on to the next digit, and we bring the 7 down. Now 12 does go into 27. It goes in twice. So we're going to put 2 up at the top, and then we're going to subtract 2 times 12, which is 24, from the 27. The green numbers down at the bottom here, we're always just showing the remainder from whatever we did to generate the digit up here. Then we move on to the final digit, bring down the 3, and we can look at dividing 12 by 33, and once again that goes in twice. And then we subtract 2 times 12 from the 33, and we end up with 9. Now the result up here gets called the quotient, and the bit down here is called the remainder. But there are specific properties to this I want to draw attention to. For every digit up here, we were only looking at the single digit that lines up with it and whatever was left over before. So for the first digit we were looking at the 2, and then we didn't have anything carried forward from before. When we got to the 7 we had the 2 and the 7, and so each time we moved the focus digit to the right we shifted up this digit into the next column, which was essentially a multiply by 10. Now, decimal is not what we want. We're looking to try and produce a machine code program for doing this. So let's take a look at the same sequence of operations in binary and see if we can understand that. Here we have the same numbers represented in binary. This equation is exactly the same as before. We've just changed the number base. And I want to look at the individual operations in the same way. So looking at the first digit, we bring the 1 down. 12 is clearly not going to divide into 1. But we need to think about what we actually mean by a divide at this point, because this is binary and we've only got 1s and 0s. We can only ever get a 0 or a 1 up here. Each time we move on to the next digit and bring an extra 1 down, the most that's going to happen is going to become twice what it was before plus 1. We know that this number before is not going to be greater than the denominator because we would have done the extra step if it was. So it can only become at most twice 1 minus the denominator plus a 1 if there was a 1 in this column. And so it's never going to be twice the denominator. So we're only ever going to divide 1 in. So we can actually talk about this in different terms. We're no longer describing this as a divide. This is simply a comparison to see if this number is greater or equal to this number. And comparing two numbers and performing a subtraction are things we've already got operations in the ALU to do. And so immediately looking at this operation in binary, we're looking much closer to the kind of things that we can feed through the ALU on the CPU. All right, let's keep going. So we pull in the next 0. 100 is still less than 1100, so that's a 0. Still smaller. And now it's interesting. This green number is now larger than the denominator. Now think about the operation here. Every time we looked at a new digit, this became multiplied by 2, or what in programming terms we can achieve with a shift left by 1, and then we've brought in this one additional bit. So now this number's larger than the denominator, so we want a 1 up there, and we perform a subtraction to gain the new remainder, which is 101. And then we move on. Okay, so that's still smaller than the denominator again. And here, once again, we've got a remainder that's larger than the denominator. So we stick the 1 up here, subtract the denominator, and we're left with the remainder. And then we can just repeat this to the end. And in the final step, our remainder here is 9, just as it was before. So here we see that division in binary is not actually more complicated, it's simpler than trying to do the same sequence of operations in decimal, for the simple reason that all of our operations here are shifts, compares and subtracts. And those are the kind of operations we've got in the ALU already. This is looking pretty good. Now, a crucial element here that I do want to draw your attention to is every single time we were looking at a digit, we were only looking at that singular digit in the numerator in order to generate the output digit in the result. And this is a particularly useful property for us to have. So if we would say dividing a 16-bit number by an 8-bit number, we don't need to look at the entire 16-bit number. We want to scan through it 1 bit at a time. Now, in the pipeline CPU, the registers are 8-bit. So rather than doing a 16-bit shift operation to pull off 1 bit at a time, we just need to look at a single 8-bit register. And then when we're done, it's the same as when we moved from this bit to this bit. We just move from 1 byte to the next. So if we code up a 8-bit divided by an 8-bit, and then we do that twice, but with the second time, instead of starting the remainder at 0, we start it at whatever the remainder from the previous operation is, we will get the low and the high bytes of the result from those sequential operations. This is a really good property for us. Whatever it takes us to do an 8-bit by 8-bit division, we can double that to do a 16 by 8 and double it again to do a 32-bit by 8-bit division. That's nice linear performance scaling, which is a property we like to see in programming. Now, before we try and translate this to program code, I just want to talk a little bit about register assignment. Now, I've spoken about wanting to do a 16-bit divided by 8-bit operation. And the reason for that is a lot of the numbers we're going to want to divide by will be 8 bits. And 8 bits are the largest register we've got. So I want to have a look at the remainder down here and ask the question, how big can it get? In the final result, the maximum size of the remainder is going to have to be the denominator minus 1. So we can start to think in terms of how big a register will we need to store this, or more importantly, if we're using a specific size register, we can back engineer that to compute what the largest denominator that we can handle is. Now, let's think about what happens before we calculate this digit here. We've shifted the remainder left by 1, so multiplied it by 2, and then we're pulling a digit down, and that might be a 1. So during the actual computation itself, the maximum size of our remainder is going to be the denominator minus 1 multiplied by 2 from the shift, and then with 1 added in the bit coming down. But what I'd really like to do is calculate what the maximum denominator can be if we're going to be storing this number in an 8-bit register. So we can store values from 0 to 255, so we have to reverse this calculation. So we've got 255 minus 1 divided by 2 and then add 1. And that gives us a value of 128. So the important thing we've done here is we've worked out that if we're storing the intermediate remainder result in an 8-bit register, the maximum denominator we support is 128. And if we know this, we can work around with it. At some point, I'll write a division that will support larger denominators by performing multiple operations for the comparison and the subtract. But this is going to be the simplest thing to do first. And if we understand the limitation, it allows us to go forward and work with it. And particularly for this first task of turning hexadecimal numbers into decimal numbers for display, this is more than sufficient. So let's have a look at some code. Okay, let's start off by defining some data. Need a quotient for the result. We'll just set that to 0. And we'll set the remainder to 0. Okay, I want to start off by doing this the most obvious way possible. Now, for those core 4 variables, we've used all of our general purpose registers. So we don't actually have a spare register to count a loop, but in most cases, for something like this where we're interested in looping a small number of times, it's usually better to unroll the loop and just put iterations of the code. Okay, so first off, we want to get the first bit from the numerator. And we want to put that into the remainder. Now when we shift, the logical carry gets added in as the extra bit. So we've got a possible unknown bit being shifted into the numerator here, but that doesn't really matter because we're just going to do this 8 times and the contents of A is redundant. So we shift up the quotient as well. So that's our base operations, and now we want to look and see if the current value of the remainder is greater than the denominator. And in our logical flow, if the remainder is greater or equal to the denominator, we want to set the bottom bit in the quotient, and we need to subtract the denominator from the current remainder value. We need to load the address. Okay, I've written JL for jump if less and, but we actually want JB, jump if below, because JL is a signed operation and JB is an unsigned operation. So now we can add our conditional function in here. So the top bit of the remainder should never be set, and that's what's getting shifted into the logical carry, so the bottom bit of the quotient after this shift should always be clear. Okay, so if we repeated this section 8 times, we would be able to divide an 8-bit by an 8-bit, and then if we replicated that another twice, but without resetting the remainder, we should be able to implement a 16 by 8-bit divide. Now, how quick is this going to be? It's 1 cycle. Also 1. So that's 4 cycles, and the conditional jump is currently 3 cycles. So that's a total of 13 cycles, and we'd be multiplying that by 8 to do an 8 by 8 divide. That's not a terrible starting point. So that would make 208 cycles to do a 16 by 8 divide, plus there'll be a few extra instructions for shuffling the data around into the right place, but generally that ballpark. 8086 has 80 to 90 cycles, so we're not terrible. And obviously these two instructions here are conditional, so that's actually 11 to 13. So we're talking 176 to 208 cycles. But I think we can do better. Now, these instructions aren't taking very much, but this conditional jump is really stacking up. So we can probably reduce that a bit. After the first label load, we can probably use an org directive to make sure that we only actually need to change TL for subsequent addresses for the skip over. That's supposed to be TX. So that would drop that down to 2 cycles in all but the first. Still quite high. I wonder what else we can do. Now when I designed the ALU, I said a divide operation was just going to be too much circuitry and I wanted to keep things simple and achievable. But I did mention that I'd be happy to add kind of utility instructions that would help us along. Let's think about what we can do. What's taking the time? We've got a lot of cycles in here. Right, so if we move the compare up, now the information that we want is actually in the carry flag at this point, because that's what the compare is doing. So if I replace this shift left B with add with carry B comma B, now adding a variable to itself is going to be the same as a shift up. It's going to multiply it by 2, but we're doing an add with carry, so it's going to bring the carry flag in, and the carry flag is going to be the information about whether or not this is less than. So that gets rid of this increment. We're spending 6 to 8 cycles here just to do a conditional subtract. Here's where I think it would be valuable to add a new instruction. So I'm going to create a new instruction that is a conditional subtract. We did a jump if below, so we want to invert that, so that's going to be subtract if above or equal D comma C. Then we can get rid of all of this. So that is a flat 5 cycles. So that would be 40 to do it on an 8-bit register and 80 cycles plus whatever extra little bits of shuffling we need to do to make it into a working function. So probably we'd get very close to or beat the 8086 if we can make this work, and that's dependent on working out a way to create this instruction. But this shouldn't be that complicated. So let's see if we can add that. Okay, I'm going to use that spare opcode. Subae, we only really need one variant of it at the moment. It's a very specialist function, so I don't think we're going to want to try and create all the variants of it. Okay, add with carry. We didn't do the versions which add a register to itself, so we need to add that. We need a spare opcode. I will renumber all of these at some point. That'll do. So this should let our code assemble. Let's create the full 8-bit divide. Add a few knobs in there so we can pause between sections of code. Now we need to implement those 2 new instructions. Okay, that one's easy. Okay, now this is not going to be very simple at all. Now that is the return to implement the subtract. Now remember, what we're doing here is building the static data in the control ROMs. The selection of the inputs is done in pipeline stage 1, as is the selection of the operation, but resolving the output is done in pipeline stage 2. This add with carry will overwrite the arithmetic carry flag when it's in pipeline stage 2, so that would take effect when this instruction is in pipeline stage 2. So whatever we're going to do to implement this instruction's difference between subtracting and not subtracting needs to happen in pipeline stage 1 before the carry flag is overwritten. That's interesting. Top 16 bits of the control word we're outputting need to be the same. So if the carry flag is set, we do exactly the same as a regular subtract. But if it's not set, we need a flag combination that won't affect the value of D, but D will get stored from the top of the ALU. So we'll AND it with itself. So we're still going to store the result from the ALU operation in D, but it will just be the same as the current value of D. And that will work. Okay, I added this useful addition to the control build program a few days ago, so it now tells me which binary files have changed, so I know it's just these two ROMs that need to be updated. Let's give that a try. Let's have a look. So here's loading 157 into A, clearing B out with an exclusive OR, and then we're loading C, 13 and clearing D with an exclusive OR. Okay, put a couple of nops in to give us a pause. Okay, so here we've got the shift left A, so that should take the top bit away from the numerator here, and that's followed immediately by the shift left D. So that bit has come in here. So here's the compare. So it's actually going to the ALU as a subtract. Then that is followed immediately by this add with carry B comma B. Now that should be just shifting up B, which is 0, so we're not going to see a change because the carry flag shouldn't be set. And then behind it here is the predicated add AE. So that's actually much more interesting. Okay, so yes, this has selected the AND operation up here, and it's selecting D as both inputs. So that's our kind of our neutral don't do anything, because a decision has to be made at this stage. And then we're back to the shift. So we should see the bits from here gradually pile up over here, and we're not really going to see any difference in what we've just done until this is greater than this. Which that should be. Here's the compare. And there's the arithmetic carry. So here's the add with carry. So we should see that first bit in the quotient set. Nice. And here is the predicated subtract function. And yes, it's a subtract over here, and the inputs are C and D. Left hand side is D, right hand side is C. This is working. Nice. Let's be bold. Okay, so We've got a result here of 12. That's correct, and a remainder of 1. Yes! We've successfully done an 8 by 8 divide. Okay, so now I want to try and turn this into a function we can call. Okay, I want to return the quotient in A because that's going to make more sense when we try and do a 16-bit one. So we'll still calculate it in B. Remainder is already in D. So we're going to be overwriting B, and C is untouched, so I think we just need to save and restore B. Okay, so how much have we added? Return is 2 cycles since we haven't used the branch delay slot. Pop is 2. Right, so we've got a total execution time of 49 cycles there. We've got our core 40 cycle divide and an additional 9 cycles of wrapping. So now for a 16-bit divide, we're going to need 2 registers for both the numerator and the quotient. Now we've got an interesting opportunity for optimization here, because in the 16 by 8 divide, if B is equal to 0, then the 8 by 8 divide is already going to produce the correct result. Now we want to do the high byte first. So I'm going to store off A and copy B into A. And then I'm going to call our 8 over 8 version. This extra test is 8 cycles, but that's already means that the address of divide 8 is loaded. So this will give us the correct result in A that should be in B for the return. The high half of the quotient is where it needs to be. We've restored the low half of the numerator. Reused this 8 by 8 divide code, but I don't want the remainder to get initialized. So I've just moved this around a bit so that the clearing out of the remainder is the first thing I do. And then, so if I jump to the label here, this should do what I need. Yeah, that will work. Okay, so going to be 3 cycles. It's going to be 4. That can probably be 2 because that's almost certainly TH is unchanged between those, but I'm not too worried about that. Okay, so in the worst case scenario, this will be, if it takes the short path, it will be 57 cycles. In the long path, it will be 19 plus 49 plus 48. So that actually compares pretty well to the 8086, considering the 8086 actually has a hardware divide instruction. Obviously more recent processors do it a lot quicker than that, but I think comparing to this kind of era processors is a bit fairer. Okay, that's excellent. I'm really pleased with that. Okay, now to give this a really decent test, I want to write a decimal output routine. That's going to take a little bit more programming, and I don't think that's something you want to watch me do. So I'm going to code that up and I'll show you the finished results in what will be a very short space of time for you. Okay, so I've coded up a demonstration of a couple of those divide functions. I had a couple of bugs to fix along the way. Writing the binary to decimal converter was a bit of a slog, took me several evenings. I'll tell you, this contention warning LED was worth its weight in gold in that process. Let's show you what I've got. So this is the Fibonacci sequence, but now it's outputting its numbers in decimal. So we can just see from the pattern of LEDs on the processor that every part of it is being worked very hard at this point. We've got a lot of different ALU operations going on, a lot of register ops, all of the registers in constant use. This is absolutely fantastic to see. I wish I could have recorded the execution of this where it first worked correctly, because my reaction would have made you all chuckle. But I am over the moon about this, and what more can I say? Well, I hope you found this whole programming experience interesting. I am aware at this point that this is quite a long video, but I think what I'm going to do is actually spend a bunch more time programming, and I'm going to construct what I hope will be a more technically impressive, to the layman, demonstration of this processor's capabilities, and I'll come back with a video demonstrating that. But anyway, thanks for watching. I'll see you again soon.